All right, let's get started. And thanks for joining me today. And today I'm gonna share some thoughts and tips on how we use Kaggle to build and ship TiKV. Let me do a brief introduction for myself. I'm Dongpo, and right now I'm a senior database kernel engineer at TiKV, which is the company behind the TiDB and TiKV databases. So actually, our website is TiKV.com, so you can check our product on the website, and all our products are open sourced. And I'm also a big believer in open source. So right now, I'm trying to help maintain the Kaggle project. And also, I used to be a member of a Rust app and the Quizile team. And you can find me through those links. And also, you can find the slide in my personal website. And today's agenda, I'll give a short, brief overview of our TiKV project, and then I'll share 6 tips from our experience. Hope those tips can help you in your day-to-day development. And then we'll have a Q&A session. I can answer any question you may have. So let's start it with a TiKV project overview. As you can see, here is a typical TiKV cluster architecture. So this is a distributed transactional key-value database. And in each cluster, we have a multiple TiKV instance. And for each instance, we'll use the Rakuten algorithm to replicate the data across the whole cluster. And also we have a placement driver cluster, which help us to maintain the metadata and also schedule the Raft groups. And for when we use this key-value database, we just throw the gRPC interface, and we build our distributed database upon this storage layer. So let's just zoom in a little bit and take a deep look at the TiKV project. So as you can see, because this is a storage layer of our database, so we have to build a high performance and a low latency system. And at that time, we decided to build our product based on the RocksDB, which developed by the Facebook in C++. And the reason we choose Rust to build this project is that for our company, most of our components are built in Golang. And our computing layer called TiDB, which 100% built in Golang. But we really want to gain the low latency and get extreme performed storage layer. So we choose to use RocksDB. But we made this decision back to 2016. So it's a quite challenge, because at that time, the Rust 1.0 just released, and it's really hard to build I guess the microphone is dead. Can you hear me? Okay, so we built a project based on RocksDB, and we couldn't really choose Golang, because even though we have a Seagull available, but use Seagull interface to interact with C++ project is extremely difficult, and also it would mess up the whole memory management. So we decided we are going to choose Rust. And because we choose Rust at that time, and we built a lot of libraries from scratch and shared it with our Rust community. So in this project, the organization name on GitHub is also TiKV. You can find all those libraries. So for example, we maintain the gmallocator in Rust, and also we built the first version of a Rust client for the Prometheus. And we even open sourced our co-implementation of a Raft algorithm. And at the same time, because we used a lot of Golang in our company. So we borrowed some ideas from the Golang community. So we built the pprof Rust implementation, which can help you to debug and inspect your CPU profiles. We even built the first version of a gRPC implementation in Rust, although it's just a wrapper of a C++ implementation. Because as I mentioned earlier, our clients need to communicate with this storage layer through the gRPC. So we decided to build it from scratch, because at that time, we don't really have the gRPC implementation. And also we built some like a fast trace crates to help us improve our observability. And we built the fail RS would help you to inject any kind of like a network errors to help you build your test infrastructure. So just feel free to check them out. I believe most of them are Apache 2.0 lessons, so you can use it in your own project. And to dive into TiKV codebase, we have more than like 500,000 lines of Rust organized in 83 crates. And it also has like more than 600 dependencies. So I think it's fairly to see Cargo plays a very, very important role in our day-to-day development workflow. So today I'm going to focus on Cargo stuff instead of the database internals. And let's get started. The first tip I want to share is that for the Rust project, we should always check in cargo.log file. And I believe for applications, this is already a standard practice. We always check in cargo.log to ensure the reproducible builds. It's almost like a by default from Cargo. And for TiKV, because it's definitely a binary, it has binary targets and also have library targets. So from the beginning, we just submitted our cargo.log from the very, very beginning. And recently, I believe Cargo also updates the policy for libraries. Right now, we recommend to check in cargo.log to ensure the consistent dependency resolution across different environments. The historical reason we didn't recommend to check in cargo.log for libraries is that we want to encourage the whole community to test your library against the latest dependencies to see what's your how your libraries behaves with the latest dependencies. But that policy also caused a lot of chaos. Because, for example, I guess you all suffered that when you have a colleague or have a contributor just submitted a perfectly valid pull request, but the CI just failed, not because his or her code. It's just because the upstream released a new version. Sometimes it's kind of like a frustrating because this would disrupt all your main CI jobs and workflows. You have to fix those issues, although those issues just came from the upstream. And that's the reason why we change our policy and recommend everybody checking the cargo.log for both applications and libraries. But as a library maintainer, you may consider that I really want to know how my library behaves with the newest dependency. So the thing we want to encourage is that you can directly set up a dedicated but separate job to do this kind of a check. You can just set, this is a GitHub Actions example. You could just check out your code and do the cargo update and then run the tests and build your library. this could be very useful to test your library with the latest dependency, and at the same time, you can just set the continue on arrow equals true, which would still help you to catch those issues earlier, but didn't really mess up your whole CI workflow. So if you do want to test it, you can have this kind of a dedicated jobs on any kind of like a CI system, I guess. And another tip is that when you set up your Kaggle project, you could leverage this feature from Kaggle called workspace inheritance. So here is the one example for the workspace inheritance package table. Usually, when you have a huge project, you need to define those common fields and metadata again and again across the whole project for each, like for almost every create. Here, as you can see, we could just define the workspace package table here and set up the authors, home pages, this kind of a basic metadata. And for the member creates, you can simply just change, specify workspace equals true. Then those member creates would automatically inherit every single metadata you defined in the workspace Kaggle.toml. This is extremely useful if you have a huge project, because you don't need to just repeat them again and again. And when you want to update them, it would be much easier, because you only need to change the workspace level metadata. So you can find the document through this link. And another one is for the dependency table. So I believe you, when you try to set up a big project, most of your creates would share the common dependencies. But it would be really hard to maintain those dependencies, especially when you have like a different feature sets or different versions. So you have to repeat those requirements again and again in those different creates. So it's pretty similar to the package table. You could simply just set the workspace equals true. Then for those creates, it would inherit the dependency definition from the workspace level. This is quite useful, at least for the TiKV project. We have a lot of dependencies. So after this feature released, we directly adapted it. This helped us to maintain our dependencies. And also, I think this would help for the even the dependency managed tools, like a dependent robot. You can, with this feature, it would be easier to review and manage those dependency updates, because usually it's end up just one line change from the global workspace Kaggle.toml. But with that being said, there's a known issue I want to share at here, because when you use this feature, sometimes it would be it has some like a surprise behaviors. Here is one example. You have one workspace and it contains two create members, full and bar. Both those two creates depend on the tracing create. But for the full create, it directly inherits from the workspace workspace level, and it works perfectly. But for the bar create, as you can see, we try to like inherit it from the workspace level, but we want to disable the default feature. But if you try to use it in this way, it would warning about the bar create couldn't really disable the default feature, because once you enabled the default feature globally, then for the member creates, there's no way you can disable it. So the workaround here is that you could actually disable the default feature in the workspace level, then you can do whatever you want in the member creates level. So I believe we are working on this issue. The reason we couldn't solve this issue yet is that this would require a behavior change and also probably a break change. So we have to wait for the next edition of Rust. But just this is something I think it's need to be aware if you want to use this feature to manage your dependencies. And after we set up the whole workspace and it comes to the cargo build. As I mentioned before, because we rely on some C++ projects. And as you can see here, we have some dependencies, just Git dependency. And most of them, some of them are C++ project, some of them some project we created or we forked from other organization. And we use a Git dependency to manage them. There is one trick we used in TiKV to help us to speed up the cargo build time, is that in cargo, there is an unstable feature called shallow depends. This feature would help you to only do the shallow clone for those Git repositories. Otherwise, it's going to conduct a full history clone, which kind of is slow, especially for this kind of Google's repository and also like a RocksDB repository. It has a very long histories. So with this feature, we can reduce our cargo build time from about 3 minutes and 27 seconds to 2 minutes and 43 seconds. It's not that huge, but when you have tons of this kind of a dependency, it can help a lot. About the cargo build, another thing I want to discuss is cargo profiles, because in cargo we have when you run cargo build, we have different profiles. For example, we have dev profiles, test profiles, and also release profiles. Even we have benchmark profiles. But I believe we all know that release build is slow, and it's acceptable because we need to do all the optimizations. But for the dev builds, I believe the speed is more important compared to other builds. So here is our dev profile from TiKV. As you can see, we disable all the optimization, and also we get rid of all the debug information, because it would help you to speed up the cargo build and also reduce the binary size from the dev build. And at the same time, we set the codegen units to 4. Actually, this is a historical mistake. I'm not sure if you spot it, because technically codegen units default right now is 256. I'm not gonna go through all those configurations. You can find those configurations on Cargo's book. So as I mentioned, this codegen units actually is a historical mistake, because back to 2014, the codegen units default value is 1. So at that time, our dev build is extremely slow, and we decided to bump our codegen units from 1 to 4, which at that time helped us speed up the build time. But because the compiler is involved, and we developed the incremental compilation feature, so right now the default value is 256. As you can see, if you bump that value further, the dev build time would reduce a lot. And I guess we changed this default value in 2020. So the point here is that once you decide to tune those parameters, you should go back and revisit the default values and the configurations from the Rust compiler, because as the compilers involves, maybe your old optimizations silently becomes like a new bottlenecks. But usually you don't need to change those values, because Kaggle would pick reasonable defaults for you. But if you do want to tweak them, you should go back and revisit them periodically, make sure nothing really blocks your dev build. And another thing I want to discuss is the debug configuration. Because at that time, like for TiKV project, if you want to build that project, it would take anywhere from 1 hour to 2 hours. So technically, you can only compile your project a few times in one workday. So we really want to improve the dev build time. So we decided, because we don't really care about too much about the runtime performance from the dev build. So we decided to turn off all the debug information from TiKV. But it turns out after we set the debug configuration to 0, we still have a very slow build time. And even the final binary size doesn't change that much. The reason is that because we have a lot of projects based on C++ projects, so we have to use a CMake RS to compile those C++ code base. And then we figured out there is one known issue from CMake RS. When you build the project with CMake RS, it wouldn't really respect your dev profile from your workspace. It has some like hard code rules in CMake RS. So the workaround here is that you can just only disable. So here we disable the debug information for the RocksDB system creates. At the same time, we enable the optimization for this library, because with this combination, you can the CMake RS would respect it as a release build. Then it will get rid of all the debug information. So here, as you can see, after we change the debug to 0 and enable the optimization level to 1, our build time actually reduced about 20 seconds, and the binary size reduced about more than 100 megabytes. So this is one trick we use when we try to build this kind of a C++ code base. And another trick we use here is that although we disable the whole debug information for the final build of our TiKV, but we still want to have the debug information for the tests, at least for the test binaries, because when there is a test failures, we really want to use the debugging tool to see what's going on. So you can directly specify the dev profile for the unit tests that would help you to enable the debug information and enable some optimizations. This is another trick we used to build TiKV. And after we build the project, I think it comes to run the tests. Here I would like to introduce a community tool help you to speed up your test execution. Let's take the Tokyo as an example. Tokyo, I guess you all know this async runtime, and it has more than 1,000 tests and across more than 200 binaries. So if you try to run Kaggle test against this repository, it would take about 200 seconds to finish all the tests. But after you leverage next test, it can just finish under 6 seconds. So it's an extreme and dramatic improvement. The reason why cargo test is so slow is that when cargo actually run the cargo test command, it would build every test binary. Those binaries are try to build your, this command would help you build all your test targets, and for each package, it would build one binary for all your unit tests. And cargo would build all those test binaries and try to run them sequentially. Even though within one single binary, we can have some concurrency, but across the binaries, across the unit tests, we don't really have that kind of a concurrency. But for the next test, it actually took a very different execution model. It split the whole test execution to two phases. The first phase is the list phase. So it's pretty similar to cargo test. It's just build every test binary, but it would do an extra step to list all the tests from those binaries. And in the run phase, it would try to execute tests process in parallel. And across the, it's in parallel, and at the same time, it's across the binaries and across the processes. So you can tell that with this execution model, we would gain a lot of concurrency compared to the cargo default test model. So it seems like we can blindly adopt this cargo next test tool in our project, but actually there is a surprise. So if you try to leverage this tool in cargo itself, you will find out that cargo next test would actually slower than cargo tests. So it's the reason is that cargo contains about 4,000 tests just across 3 binaries. The reason is that we, in cargo project, we only write end-to-end integration tests. We don't really have much unit tests. So it ends up only in concentrated just in 3 binaries. And then, as I mentioned before, there's no much concurrency you can gain, right? So at the same time, it's not only slower than cargo test, but also you can see here more than 50 tests just failed. The reason is that cargo tests actually relies on shared states, which cause failures when you try to run in parallel across the binaries. Because for cargo, most of those tests are try to reading from disk and writing to disk to update those cargo toml and all the manifest and all the stuff. So technically, if you try to run those tests across the binary, it would just fail. So it really depends on your project test structure. You should evaluate before you introduce this to your project. Because if you only have a unit test in your project, then cargo next test would extremely help you to reduce the test execution time. But if you do have a few integration tests and also those integration tests share the states, that means it's not even help you to speed up, but also just will fail your test and break all the shared states. And as I mentioned, cargo's tests are all integration tests. So there is an addition trick you can play here. For example, here is one project which contains two integration tests. We put it under the test directory, so cargo would respect each file as a dedicated integration test. And after you build the project, try to run the tests, it would end up 2 binaries for each file. So this kind of like a structure would slow down your test execution, but also slow down your build time, because you have to generate the test binary separately and also run those tests sequentially. And the one trick here is that you could simply change your structure to this way. You can avoid to put each file as an integration test under the test directory. You can create a subdirectory, maybe we can call it test suite. And under the test suite, you can define a main IS file and try to put those tests as modules of this package. And then the cargo would help you only build one binary for those tests. At the same time, because we have that, like within one binary, we have the parallelism. So it would not only speed up your build time, but also try to run your tests in parallel as much as possible. So this is another like a trick we use in TiKV to help us speed up our test execution. And after we build the project and run all the tests, the last thing I want to cover is linters, because when it comes to the long-term maintenance, linter is very important. So in TiKV project, we try to use linters as much as possible. I guess you all very familiar with the clip, and I believe most of Rust agents would use clip in their day-to-day workflow. But here I want to share some extra advantage features from clip. So for example, in TiKV, we don't really allow the developers to use the standard thread builder spawn function, because we want to do extra checks and bookkeeping when we create any thread from TiKV. So we could leverage the ability from clip and convert this kind of conversions into the linting system. So here we can just disallow this API and give a reasonable, good reason for the developers and encourage them to use the right API. So this kind of stuff is pretty helpful if you want to have a project-specific rules. And also you can easily enforce this kind of rules across the whole team. And also it applies to the types. You can find more this kind of advantage features from a clip through this link. And as I mentioned before, TiKV is an open source project. So we really want to because we use Apache 2.0 license. So we have a very strict license policies. And you couldn't really ask all your colleagues or all your contributors to respect those license rules, because nobody really understands what's going on under those, like a bunch of license. So you could leverage a community tool called cargo deny. And with this tool, you can specify a allow list which compatible with your own license. And then every time you build your project or you add a new dependency, the cargo deny would help you to check your dependencies against this list. So this is pretty useful for the open source project. And another useful feature from cargo deny is that because we forked a lot of projects from other organizations, and we only really want to avoid depend on trust third-party code. So you could just specify for the unknown Git dependency, it's to forbid the unknown Git dependency, and at the same time you can forbid any code from other registry. You can even specify the allow organizations. Then every single Git dependency could only come from these three organizations. And I believe cargo deny also have much more features. So you could just check out this tool to see if this tool can help your project. And another thing I want to mention is that for the workspace inherency, we already covered the package table and the dependency table. But here we also have a dedicated lint table. So you could define some lint rules, maybe from the Rust compiler or from clip, and put it in the global level in the workspace cargo.toml. And then you can just simply inherit it from the members creates. Then you don't need to repeat those lint rules again and again. But also you could have specific lint rules for some of those create. And you can find the document through this link. I guess I would just wrap up my talk by looking at what's coming next. So right now, the Cargo team is working on a cargo linting system. Here is one example. This linting system is pretty similar to Rust compiler lint system and also the clip lint system, but this system is dedicated for the cargo itself. So you could control and enforce some best practice in the manifest level. This is one example. You just have a lint table dedicated to the cargo itself, and you could set a lint rule, try to warning about the minimum version requests. So when you run this, run the cargo build under this project, it would emit a warning to see that dependency version requirements without minimum version. So it also gives you the very useful help message to notify you how to fix this issue. So this kind of a linting tools is pretty useful, and it can help you to apply all the best practice across the whole workspace within the manifest level. So this feature is still under the development, and you can follow this GitHub issue to get updates. I guess that's what wraps up my talk, and I hope those tips can help you and you can apply some of them to your own project. Thank you for listening, and do you have any questions?